Let's see, so let's look back at normal forces. Remember normal forces. So I'm getting lots of questions. Dr. Stinson, we posted the rooms on Canvas, or we emailed them, or what did we do?
I haven't posted them yet.
Okay.
I was posted on Canvas, and then I'll have to go to email them.
Yeah.
Yeah, so I'll post it on Canvas.
Yeah, it's like we don't know until the registrar tells us, or until the registrar tells us we're there. So I think we're still waiting to find it. But Canvas will tell you which room to go to by your last name. Okay, so remember this, say we normal force here, so say you got a thing there, I'm going to bring out a piece of metal here, right, and say you got a block on it like this. Something like that, right? And we do sum of the forces y equals 0 because it's static, what we just did, right? mg is pulling it down, but there must be a normal force pushing it up. Right, so the normal force equals mg. This standard situation that the metal is pushing up with the normal force while the mg pulls it down. Right? And we talked about before, how does it know? Like when I push down the table, how does it know to respond the right amount? It's a little bit weird, right? It's like you think the table's actually thinking about it. It's like some of you are bioscience people, right? You're going to find biochemists, they think that the molecules like have free will and like a conscience. They say, well, this ATP receptor decided to go over here. Well, it probably didn't. There's probably another explanation. So here, the other explanation is it's like a spring. So normal forces are due to small deformations. And remember, we're going beyond rigid bodies now. Now we're talking about deformable bodies. All real bodies are at some limit deformable. So when I push on that table, the reason it can respond, or when this mass pushes on this piece of metal, the reason it responds is it's basically equal to this, where the metal is like a great big spring like that. Right? And then it's sitting on it like this. So these are basically the same thing. The metal that's applying the normal force is just acting like a huge spring. So we could actually write then, we could use Hooke's law in a way. We could say, I guess I want to say that K delta X equals mg. Now this normal force that we said just some magical force that comes out of the metal is really the metal acting like a spring. And negative just because it balances mg. Don't worry about the sign. We're just doing magnitudes right now. K delta X equals mg. So what you would find is if you put sort of a typical numbers in here, that K would be very large. Like 10 to the 7, I think is what I wrote down. Yeah, about 10 to the 7 newtons per meter. Huge number. Therefore, if say you put a typical, 100-gram weight on a metal cylinder, you'd get delta X very small. 10 to the minus 6 meters. Something teeny like that. So that's why we don't notice. They are spring forces, but just the deflections, the delta X's are so teeny you don't detect them. Right? 10 to the minus 6 meters is 1/100th the width of a human hair. So you're not going to notice that. So normal forces, but then you might say, except, what's the one way you can't apply this? It's not exactly like a spring because it's not attached. Right? It's only like a spring halfway. Like a spring, only under compression. You can only push it, you can't pull. And then, we won't do it now, we'll take our break. But it's basically the same thing for tension. Right? Tension, you can treat the rope like a spring, you pull it and it pulls back. But you can't compress a rope. So it's basically the exact same thing, it's just for extension rather than compression. So these mysterious forces that we gave you no insight on, normal and tension, are really just like spring forces. So if you consider the bodies deformable. Okay, so let's take our break and then we'll do whatever.